So if we have two waves that are out of phase, so that one has moved across a little, then when we add them together, we'll get a positive part of the wave added to a negative part of the wave, which will produce 0. So the two waves are completely out of phase, and this means that they'll have destructive interference. They won't construct a bigger wave, they'll destroy each other. So we can see what that looks like right at the bottom. As you can see, a cancelled wave is very boring. So the new wave's amplitude will be 0 all over. It won't really be a wave anymore. In other words, both of the original waves have cancelled each other out, so they no longer exist. So destructive interference means that it's possible to destroy a wave by playing an identical wave at a slightly different delay, so that one wave is just slightly ahead of the other wave. So it turns out that if we have two sine wave sound waves, which are very boring but very easy to work with, then we can in fact show this effect. It turns out that in different locations in front of the speakers, the sound will get louder or softer. When we have two crests overlapping, such as where these lines intersect, we will get constructive interference and the sound will be a bit louder. If we get spots where there's one crest and one trough, that is somewhere like this or this, then in these cases we won't be able to hear the sound because the crest of one wave is overlapping with the trough of another and they are cancelling each other out. So this corresponds to areas of constructive and destructive interference. You can imagine that if we're building a concert hall where you hear orchestras or bands playing music, then the people who construct the hall will have to be very careful to build it so that we don't get lots and lots of spots where destructive interference can happen for lots of different types of wavelengths. This is a superposition of two smaller waves. Given that this is one of the waves, figure out the other one. So in this case, instead of adding two waves together, we're subtracting this wave from this much more complex wave in order to get a smaller wave. That makes sense? What we need to do is figure out a wave that we can add this to make this pattern. So let's look carefully at this. Right at the start, this wave moves up from the x-axis in the positive direction. And this complex wave does the same thing, but it gets to about twice the amplitude of our smaller wave. So that means that the other wave that we're looking at must do something similar, right? But we also know that almost straight away, this wave drops down to 0, and this wave takes a little bit longer to do that, but it also drops down to 0. That means that the wave that we're looking for will turn around quite quickly and get back to 0 close to that point as well. Well, what happens next? You can see that we have a couple of wavelengths on the right side, and we have a couple of wavelengths on the right side here as well. So at the moment, we're looking at this part of the wave. We have 3 crests and 2.5 troughs, or rather 3 troughs and 2.5 crests. And we can see that these will correspond to these 3 troughs in our big wave. The crests are over here. That means that the missing wave will have to go in between these to make a pattern something like this. We can see that the wave is symmetrical, so a similar thing will happen on the other side. What then does our wave look like in the end? Well, it should be something like this, which isn't perhaps quite the wave you were expecting, but it certainly follows from these two parts of the question that this is the only possible wave that could make a pattern like that one.